Thank you, Jayesh. And thank you, ISRO and Dr. Praveen for providing an opportunity to give a talk on a very interesting topic, solar system formation and evolution. So as you can see here, the solar system, our solar system, consists of the sun, the inner planets, which are Mercury, Venus, Earth, and Mars. And then, of course, you have asteroid belt, and then the outer planets, Jupiter, Saturn, Uranus, and Neptune. And then there are dwarf planets as well. And Pluto happened to be considered a dwarf planet in recent times. So let us start. And you can see a picture of the terrestrial planets, so the inner planets, Mercury, Venus, Earth, and Mars. And what you see is, and maybe many of you have wondered, why only on Earth do we have life? Why did Earth evolve in this manner? And why do we have such a beautiful planet in the solar system where the life evolved, primitive life evolved, and then humans exist in this planet, whereas everywhere else there are difficulties in the atmosphere, or they are devoid of magnetic field, and therefore it is difficult for life to have survived, except in a few satellites, and in the case of early Mars, but that is still being debated. So here you can see Mercury and then Venus, and why Venus and Earth look almost alike, but why did they follow such different paths? Was Venus like Earth? We may question, say 4 billion years ago. And also Mars, which has a 6 millibar atmosphere, is known to have a thicker atmosphere. And did life exist on Mars? These are some fundamental questions, which one can ask about the solar system. And this is what we are interested in learning when we explore the solar system. We wish to know, how did they come to its present state? So the solar system objects range in size from a few microns, which is basically dust, to giant planets. Information exists at all scales which tell us about the origin and evolution of planets. Now, as you are aware, in 2006, the Astronomical Union has brought out a very well-defined concept of a planet, which is basically, it should orbit around the sun, should be sufficiently massive and has a spherical shape, and it should have cleared region around its orbit of large debris. So therefore, since Pluto does not satisfy the third criteria, it is considered as a dwarf planet, as is Ceres. And then you have the asteroid belt between 2.2 and 3.2 AU, and then the Kuiper belt objects, icy remnants of the early solar system. They represent residue from the planet formation process and have undergone thermal and/or chemical processing. So here I'm showing certain physical properties of the bodies, objects in the solar system. And you can see that I have given different colors to the planets and the dwarf planets. So you have the inner planets, Mercury, Venus, Earth, and Mars. I talked about the dimension of Venus and Earth, and you can see that the radius is almost similar. Just 5%, Venus radius is 5% smaller than Earth's radii. Mercury is smaller, and Mars is 3,390 kilometers. And then you have the giants, the gas giants, beyond the in the outer solar system, Jupiter and Saturn, and then the ice giants, Uranus and Neptune. And Pluto is now considered a dwarf planet alongside Ceres, Psyche, and Vesta. So amongst the dwarf planets, you can see the Psyche is just a 111-kilometer body, okay? And Vesta is 262 kilometers, and it has been linked with the meteorite group, the HED meteorite group. And then you have Pluto, which is 1153. It is much smaller than the other planets, and its size is 1153 kilometers. The masses are also given, and as are the densities. So you can see the terrestrial planets have much higher densities, and because they're rocky planets, right? So densities. This is the bulk density, and they range from around 5.5 to about 4, and then in the case of Earth's moon, the bulk density is 3.3, but at the surface, because it's porous, the density is only about 1.6 or so. But this varies depending on where you are. And then you have the gas giants and the ice giants, and you can see a difference in the density. It's 1.33 for Jupiter, which is mainly hydrogen and helium, and so is Saturn. And then in Uranus and Neptune, you have volatiles, okay, as well, as will be shown later. The semi-major axes are shown here, and then gravity. So Earth's gravity, as all of you know, is 9.8 meters per second square. And one can calculate, all of you can calculate the escape velocity, which is square root of 2 gm by r, and it happens to be around 11 kilometers per second for that of Earth. And you can similarly calculate from the mass the escape velocity in meters per second square for some of the other planets. The temperatures also tell you something about the planet, whether you can survive or not. And Earth has a very, this is the average surface temperature. But in Mercury, the range, fluctuates from 100 to 700 because it doesn't have an atmosphere. So therefore, at night, temperatures can be as low as 100. And in fact, there are regions where volatiles and ice are stored on Mercury, and also on Earth's moon. And then in Pluto, in the ice giants, you can see the temperatures are much lower, well below 0 degree, and of the order of 76 for Uranus, 72 for Neptune, and then the orbital days are listed. I would like to tell you the astronomical unit is 150 million kilometers. This is the average distance between the Sun and Earth. And this is used in several terminologies to describe this orbit of a satellite or a moon or a planetary object. So here, I have listed some of the satellites, some of the larger satellites. So you can see the largest satellite here is Ganymede, which is, and Moon is left there because for a reference. And Ceres and Pluto are dwarf planets, okay? And the masses are also given, and then bulk densities are given for the satellites. And the next slide shows you the surface temperatures. So this has been given. The surface temperatures for Jupiter, Saturn, Uranus, and Neptune are listed at 1 bar. This is the base of the atmosphere, basically. And then the magnetic field, which is shown for, the Earth is shown there. And the magnetic fields, Mercury has a small magnetic field of the order of 300 nanotesla, but Earth has a significant magnetic field. So on the sunward side, as you know, because of you have a magnetosphere. This has been discussed in other lectures. So I will not dwell on it too long, but on the sunward side it is compressed, and then it extends, on the other side of the Earth to large distances. Now, the Jupiter, you can see that there are significant magnetic fields for the planets in the outer solar system, and of the order of 420 microtesla for Jupiter, and then of the order of tens of Tesla for Saturn, Uranus, and Neptune. The surface pressures are listed here, so one can, have a rough idea. All of you know that PV equals NKT, right? So from that, if you use the pressure and the Boltzmann's constant, then one can calculate the number of molecules per cc, and you will find that for at the surface of the Earth, which is the atmospheric pressure is about 1 bar, you will have 10 to the power 19 molecules per cc. But on Mercury and Moon, it reduces by a factor of 10 to the power minus 14. So you'll have 10,000 to 10,000 molecules per cc, and this is what is seen. The major species are also listed here. Mars has a surface pressure of about 6.5 millibar, and Venus is, of course, is different. Venus has, as I showed previously, it has a surface temperature of 740 Kelvin, and then a pressure of 93 bar, dominated by carbon dioxide. And this has happened because of the runaway greenhouse effect at some point of time. So basically, once the oceans evaporated, then more and more, because of the presence of gas, the heat was trapped, and Venus became extremely warm, and it is difficult to survive on the surface. Now, the atmospheric composition is listed on the right-hand side, and these are, you can see that Venus is dominated by carbon dioxide. Mars is also dominated by carbon dioxide. Whereas Earth, a habitable planet, you have nitrogen, oxygen, and then argon and carbon dioxide, which is responsible. Carbon dioxide is primarily responsible for the greenhouse effect, but it increases, it is under control thus far. And then you have the outer planets, where you can see large concentrations of hydrogen and helium, right? Which is the main thing in the sun as well as in the solar system. But then you have also ammonia, and then you have methane in the ice giants. And Pluto, the composition is nitrogen, and then you have trace components of methane and carbon monoxide. So how did the solar system form? So this is shown here. So star formation begins inside a dark interstellar molecular cloud, which collapses. Basically, it contains high density regions where you have 10 to the power 4 molecules, 10,000 molecules per cc, which is about 1,000 times more than the most rarefied regions of this molecular cloud. And then this is gravitationally unstable, and it basically collapses under its gravity. Because of gravity, it collapses, and there is a gravitational collapse, which you can see. Once it collapses, then you have rapid accumulation of mass from a circumstellar disk, and then you have the formation of a protostar, and then you have a disk around it, and you have a lot of dust and gas which is surrounding this disk. So and then you see, so you have the protostar which is formed. This is from, and then you have the formation of the protostar, and then the protoplanetary disk. And this once the dust basically dissipates, dusty disk, what happens is that the object becomes visible as a T Tauri star. You know, the young, this is the younger phase of a sun-like star, and it's very active at this phase, and there is a protoplanetary disk which has been seen. You know, this is visible in optical wavelengths as well, and it has been seen by observatories. And then you also have bipolar flow, and then finally, you know, this is still a pre-main sequence star, but in a sun-like star, then it, you know, the core is contracting further, and at some point of time, the temperature rises to about 10 to the power 6 Kelvin or so, where thermonuclear fusion can start, and it, you know, this, and then the star goes into the main sequence, and you have a planetary system which has formed outside from accumulation of planetesimals. So this is how the solar system forms, and this is also shown here. So basically, once again, you know, you have a small part which is a small region of a giant molecular cloud which is collapsing, and it is surmised that this may be due to the shock wave of a nearby exploding star, which is a supernova. And then the spinning motion flattened the disk, and so you have this you know, accretion disk of dust and planetesimals, and then these, basically the planetesimals will accumulate slowly, form larger and larger bodies, and there will be remnants which will form the asteroid belt between Mars and Jupiter. So this is what I've discussed here in this slide. And from this disk, which is there, you know, around the protostar, you have the formation of planets, dwarf planets, and large moons. In some cases, the planets did not form, and therefore you have bits and pieces which you know, which constitute the asteroid belt. There are different asteroids there which one wants to explore to understand, and they basically store information about the early solar system, because, you know, some of them can be linked with meteorites which have fallen on Earth, and then there are other small leftover pieces which become asteroids, comets, meteoroids, and moons. So this is a picture of the outer solar system, and you can recognize the different bodies. So nearest to the sun, only rocky material could withstand the heat in the early solar system. Thus, the 4 planets, Mercury, Venus, Earth, and Mars, are terrestrial planets, and they have solid rocky surfaces. But once you, you know, things start becoming cooler, right? So therefore, if you look at the TT diagram of water, for example, you know, then you'll see that once you have low pressures and low temperatures, basically sublimation occurs, okay? So gas can condense to form solids, you know, without going into the liquid phase. And therefore, you have accumulation of large amounts of materials in the outer solar system, and they form the gas giants, Jupiter and Saturn, and then the ice giants, Uranus and Neptune. So asteroids and comets have origins from the solar nebula and provide samples which are suitable for dating the formation of the solar system. And meteorites originate mostly from the asteroid belt, but they are also from Moon and Mars. And some meteorites are derived from asteroids which have experienced differentiation. So basically, I will explain this when I discuss the lunar evolution. Basically, heat of accretion results or radioactivity. Okay, so that results in melting of the body, and then the heavier minerals will sink and the lighter material will float, and this is called differentiation. So you basically differentiate a body. Okay, but this will only happen, and the isotope which is relevant here is aluminium-26, okay, which is a heat source. for kilometer-sized asteroid bodies. So chondrites, this is a kind of meteorite. Basically, they contain this is very primitive material, and they contain spherical chondrules of olivine and pyroxene grains of the order of 0.1 to 2 millimeter in diameter, and basically they have been formed because of flash melting. They said from their morphology, one suggests that they solidified from a melt. And then you have a group of meteorites, the HED meteorites, the Howardites, Eucrites, and Diogenites, which originated from a single parent body, 4-way star. This has been linked. One can actually, if there was a mission, and you can look at the reflectance spectroscopy of meteorites and the parent body, and then you can actually determine the chemical composition, using X-ray or gamma ray spectroscopy, and then compare that with the meteorite's composition. That way you can link asteroid meteorite link. This is a major thing in planetary science research. How do you, where are the meteorites coming from? Okay, so, and irons have originated from the cores of asteroids that broke up. This is also a kind of meteorite, but can be a result of an impact melting as well. Planetary bodies formed by accretion of grains that condensed from nebula, and then, as I said, centimeter-sized objects grew to meter-sized objects and kilometer-sized planetesimals. So collisions and further accretion made larger bodies of a few thousand kilometers. So there are some fundamental questions which I've just thrown here. This is just a few. There are many which many of you must have wondered sometime when you did science. Why life originated only on Earth? How did Venus acquire its dense atmosphere? Why Mars has a very thin atmosphere? This is a main question which was addressed recently in recent missions to Mars, and then why Moon has no atmosphere. So now the inner planets, you should know, are called terrestrial because of their rocky composition, and they have bulk densities which depend on the metal content, and they have remnant fields, or they have internally generated dipolar magnetic fields. Basically a dynamo effect, and this must have been discussed in some of the lectures earlier as well, particularly the Earth's magnetic field and the Earth's magnetosphere. Gas giants are composed of hydrogen and helium cores, probably rocky, and have strong magnetic fields. And then the ice giants have mixed rock and ice cores, which are overlain by oceans of ammonia and atmospheres of hydrogen and helium, and they possess active magnetic fields. Now I'm moving on to the next part. So this was about physical characteristics. This was the first part. This was about physical characteristics of the solar system, formation of the solar system, evolution, initial evolution of the solar system. And now I'm moving on to a little bit about meteorites. And PRL has a very strong legacy in terms of meteorite research, and I hope to show some of you, I hope to show some of that research here in the next 10 to 15 minutes. And then the last part of the lecture will reflect on two large objects, in the inner solar system, relatively large, Moon and Mars, and some exploration which has been done recently, particularly in the last 2 decades. So the first, solids to condense, you can see the condensation temperature sequence, right? So I've listed the material and then the composition. Okay, so corundum is aluminum oxide, perovskite is calcium titanium oxide, then spinel, olivine, these you would have heard of, these are found everywhere, anorthite, feldspar, triolite, magnetite, and volatiles are a little more rare, okay, unless the planet is cold, relatively cold, or the object is relatively cold. It is difficult to find volatiles. So the condensation temperature is shown. So the first solids to condense, as you can see from the condensation temperatures, where refractory, so high melting points and low vapor pressure in nature. So, and they occur as inclusions in meteorites. So, so the first set of solids are called calcium aluminum inclusions. Okay? And the aluminum 26 composition has been measured in calcium aluminum inclusions. And from that, the relative, from the early solar system history has been deduced by looking at the isotopic ratio, and this I will highlight. This is based on radioactive decay law as well, which you know, n equals n0 e to the power minus lambda t. Lambda is the decay constant, Ln2 by the t half, which is t half is basically half-life particular isotope. So from this, one can deduce the relative age, okay? And then you have long-lived isotopes. You know, for example, uranium-238, which is a half-life of 4.5 billion years. From long-lived isotopes, you can also deduce the age of the first-form solids. Now, chondrule is one of the first-form solid, as I said, but it came after Ci, and even that was debated based on aluminum-26 systematics. And chondrules present in undifferentiated meteorites, just that melting occurred soon after the condensation of first solids. Right. So this is a carbonaceous chondrite. This is Allende. This is the largest one, in fact, fell in Mexico. And you can see a calcium aluminum inclusion inside Allende, right? The size is not labeled here, but this is one of the first condensates in the early solar system. So and this is highlighted here. You see primitive meteorites. So I've shown the initial material. In that you have refractory silicates. Okay, and then you have chondrules, but then you also have from the fragments of processed asteroids. So you have achondrites have come from that. Okay, so these are melted and recrystallized, and you also have stony iron and iron, which come from the cores of asteroids. Okay, mantles and cores of asteroids, inner part of the asteroids. So the idea is that can we tell about the processes and the early, time scales of the early solar system. And for that, you need to know first you need to know different kinds of meteorites. So chondrites are basically undifferentiated primordial matter, and OL and PX. Okay, so this is olivine and pyroxene, ferro-magnesium silicates, so iron, magnesium silicates. Okay, which have condensed from hot solar nebula to form small spherules. But you also have achondrites. So these are formed by accretion and differentiation of larger asteroids. Okay, so the first part, carbonaceous chondrites, particularly, very, very primitive material. Okay, and then you have the stony iron meteorites and the iron meteorites, which are mostly composed of iron, nickel and iron metal. So the percentage of relative abundance of falls are those which have fallen on the Earth. I have listed, and this is categorized in terms of undifferentiated and differentiated meteorites. So you have three classes: stones, stony irons, and irons. So amongst the stones, you have chondrites, which is, you have carbonaceous or ordinary enstatite, and then you have R and K. So enstatite, chondrites constitute 86% of the falls, and achondrites about 9%. And amongst the achondrites, these are differentiated, so melted, recrystallized. And these are primitive. There are primitive achondrites as well. And then you have asteroidal and lunar and Martian origin. And then you have others as well, pallasites and mesodorites, which are basically stony irons, okay? And then you have, so they're rich in iron and nickel. And then you have magmatic and non-magmatic irons. So how do we study them? So our samples are primitive meteorites and planetary samples, and we use mass spectrometers and radiation detectors. So there are several instruments which are basically mass spectrometers, an ion microprobe and nano secondary and mass spectrometer were particularly used to tell about the timescales of the early solar system. And I hope to show you some examples here. Basically, and you also need in some situations, particularly in the case of meteorites, you need to study the gamma rays, which are emanated from the meteorite, and then sample characterization is done using an X-ray fluorescence spectrometer and inductively coupled plasma mass spectrometer. Mineralogic elemental is done using electron probe microanalyzer by looking at the X-rays. Okay, so important parameters for studying. So now I will highlight the method, how one can tell the timing of the relative timing of an event in the case of an early solar system. And this is based on, you have to identify the proper planetary sample. So it should not have been reprocessed. And then you need to know you need to use appropriate radionuclides. So this depends on the half-life. So if you wish to date an event which is 10 million years after the solar system formed, it is difficult to use an isotope which has a half-life, going beyond 6 or 7 half-lives. As you know, you will have significant decay. So and it will become extinct. So depending on the half-life, for example, aluminium-26 is an isotope which has been used to date chondrules. So the half-life is 0.72 million years. So you can go, you can date events which are a few million years old, but it's difficult to date an event which happened 10 million years after the solar system. And you have to determine the elemental and isotopic abundances to decipher the details to tell about the process. So this is showing, you see. So I talked about this, right? So aluminium-26, 27 is stable. Okay? 27 is stable, but 26 aluminium decays to magnesium-26 with a half-life of 0.72 million years. And then you have 3 stable isotopes, okay? So basically, in the next slide I will show, so from this, by looking at this decay, okay? So after, suppose aluminium-26 was incorporated into into a chondrule, okay, which is present within a meteorite. Now, this aluminium-26 would have completely decayed after 7, 8 half-lives, but it will no longer be there after some time. But its decay product, magnesium-26, helps us to tell the relative age. And this is highlighted here. So you have the cloud collapse, as I showed you earlier, okay, and which forms the sun. And then within 1 million years or so, the first solids are formed. This we know, the refractory oxides and the silicates which condense first. Okay, so those are forming there. Then you have the chondrules. Okay, so what is the time after the formation of the calcium aluminum inclusions? Okay, which are the first formed solids in our solar system. What is the time gap Okay, and this we can tell. You can see there. I've listed. This is worked out. This is basically, you can work this out from the decay law. Okay? So delta T1 is equal to lambda inverse. So this is the decay constant, and I have calculated that for you. And one needs to know the ratio of 26/27 in the CAI and in the chondrule. Okay? So these are measured using SIM, ion mass spectrometer. Okay? And then from that, see, this is Ruth Goswami and Goswami's, Jane Goswami's work. This was a paper published in EPSL. If you look at that equation on top, basically from this, you can work out the initial value. This is what you need of aluminum 26/27, initial value in the chondrule. Now we know that the initial value for the case of CAI, 26/27 is 5 into 10 to the power minus 5. Okay, and this, so from that, one can deduce using the previous equation. From this equation, you can see here, okay, these measurements have been done, and the slope of this graph basically gives you 26. This is y equals mx plus c, right? So you know this. So c is the initial value of 26/24, and then the slope, which is m, is 26/27 initial. So that is how you deduce this, and from then, if you know the 26/27 initial ratio of CAI, and of course this assumes that initially the composition was the same. That is a basic assumption, and this has been shown in many different phases of CAI, that this assumption is correct. From this, you can deduce the time frame, and that shows that chondrule in fact forms. You can see here, this is this is from Huss's paper, and you can see here, right? So this is 26/27, and this is 5 into 10 to the power minus 5. So here, these are the measurements, which are there for, this is for CAI, and this is for aluminum chondrules and ferromagnesium chondrules, all these ones. There are many of them in different kinds of meteorites. This is metamorphic grades, so basically they've been processed. You can say, they have undergone more and more processing, right? So as you go up, so these are many different kinds of meteorites, and you can see here, mostly they fall in this range. And it was deduced that the chondrules have formed between 1 and 3 million years after the solar system formed from these measurements. Okay, now I come to the concluding part of my talk. So this is regarding Moon. So I will not discuss every planet, because the outer solar system requires another lecture, and it is far less explored. So therefore, we will not discuss that. Venus, all I will tell you is that there have been, it's difficult to explore Venus because of the conditions, but still you had Venus Express and Venera and Magellan, which have provided data, and they tell us certain things about Venus, and particularly the conditions, and then the surface of the Venus and atmospheric, and about the atmosphere of Venus. And 50 kilometers above and I can tell you that 50 kilometers above the surface of Venus, you have conditions in the atmosphere which are like that of Earth, except that for the composition, because you have those, you have sulfur in the atmosphere, right? So you have, that's why that yellow color is there. But here, let me point out that in the case of Moon, this was a major site of exploration, and I will show you all. I will just show you a list of the missions, and even now, it is a major area of research, as you will see in the concluding slide on Moon. So the first idea was, the first research question which scientists thought about was that how did the Moon form? So basically it was concluded, there were many theories, but it was concluded that a Mars-sized object impactor hits the Earth, and it basically blows out debris which goes into orbit, and then it accretes from the Moon. This provided a correct angular momentum, so it solved the angular momentum problem. And it also solved basically the isotopic composition. If you look at the oxygen isotopic composition of the Moon and the Earth, they will fall on the same line. So that told us that Earth and Moon are connected, right? So on the other features, the observational features which were explained was that only the outer mantle and crust of Earth are involved, so therefore the iron content can be lower. And this was a glancing collision, and therefore the volatile elements and Moon and water is almost gone, although recently you've seen from the M-Cube experiment on Chandrayaan-1 that Moon does have water ice present in significant proportions, and more so in permanently shadowed regions of the Moon. We think that it is a repository of volatiles, including water. And then this is followed by the heat of accretion, which causes melting of the outer surface. But then there are questions regarding this as well, which I highlighted in the study material, and you can go through that. Questions regarding creep, which was the last residue. Basically, there's a region where the uranium and thorium concentrations are much higher, 10 ppm thorium, 3 ppm uranium. So why, one is, this is of course a heat source, but then is there any other heat source? And this was highlighted upon in recent research as well, even from our group, and then from a recent mission sent by the Chinese. So now the Moon forms around 4.56 billion years ago. So you have accretionary melting, which results in a magma ocean, and most of the Moon melted. And crystallization of the magma ocean forms the feldspar ridge. So you have basically differentiation, which I discussed. Heavier materials sink. Okay, and then after that, you have impacts. They saturate the lunar crust, and then you have basins of all sizes formed. And you must have seen this in the beautiful pictures of Moon, which are there. And then you but cratering rate, whether it reaches a peak or not, this is also whether it continued and how long it continued. This is debatable, particularly in the early part of Moon, because we Apollo sampled a part of the Moon, okay, Apollo and Luna. So we don't have ages which tell us about the entire time scale of lunar evolution. So there are more sample return missions which are required, and I will highlight this in the next slide. And then there was a period of major volcanism. So where is this heat source? So this is being debated, whether it was creep or non-creep as well. So for that, we need more samples and more additional determinations of uranium, thorium, and potassium, which are the major radioactive elements. And we need to know the concentrations in different regions, and only then we will be able to discuss this theory which has come regarding non-creep source of volcanism. And then you have, of course, mature surface more or less, and of course, young volcanism is there. So this is now showing you, one M-cube looks at the water, which is in the top, in the first few millimeters, right? But then there are also rocks which have been collected. So this is Apollo 15 rock, apatite. Okay, this is basically a calcium phosphate. In that, if you use nanosims, EPMA, you can see this is a picture basically. If you use nanosims, one can measure the water content, and it is shown to be a few thousand ppm level, using the nanosecondary and mass spectrometer. So water does exist in Moon, and this has been shown in recent in the recent experiment. This was the major discovery from Chandrayaan-1, and then also it is also seen in certain Apollo rocks as well, that water exists in several concentrations. Now, this is highlighting another aspect. If you wish to know the chemical composition, so how do you know? So Moon doesn't have an atmosphere, right? 10 to the power minus 14 bar, so 10 to the power 5. So therefore, because there is no atmosphere and there is no magnetic field, so therefore the cosmic rays just come in. They're not deflected, as in the case of Earth, and then they go inside they will penetrate the surface, and then at some point there will be a nuclear reaction for GeV protons, which are the primary protons, okay, and produce neutrons, and these neutrons then transport, and they will produce epithermal neutrons, with basically neutrons, they don't have charge, so they will not have electromagnetic interactions, but they'll be moderated, so they will lose energy, and then there is a neutron albedo. So basically, you have neutrons escaping. Some neutrons will escape, and this is the radiation. But they will also undergo reactions, and you can see uranium, thorium, potassium giving gamma rays. But N gamma and N gamma reactions are there as well. So this next slide shows you a process and certain lines, prominent lines, okay. Alpha line, which is basically 5.4 and 5.3, which can be used to construct the volatile history if these measurements are done at various locations on the Moon. And then you have uranium, and then one of the decay products is radon in the uranium-238 decay series. So this is a half-life of 3.8 days. It's a gas, it's a volatile, it diffuses, and then it will finally escape, and then some of it will escape, and then it decays to polonium-210, and then it gives that alpha particle, which you see there, and then to lead-210, okay, through a few other decays, and then further down the chain, you have, after a beta decay, you have polonium-210, right? So you have 5.3 MeV alpha, 5.49 MeV alpha, and 46.5 keV. So if we see an excess of these lines, excess intensity, compare in the polar regions compared to the equatorial regions, one can certify the volatile transport which is occurring on Moon. Now, these are the missions, okay, which are listed here. So I've listed orbiters, which are listed in red, and there's one CubeSat there, and you can see that after the Apollo and the Luna missions, Moon was not explored for a long time. It remained unexplored until the Clementine mission, which actually suggested ice, but it was not conclusive from the bistatic radar experiment. And then you had the lunar prospector also, that had a neutron experiment, epithermal neutrons. There was a decrease in intensity in the polar regions. But the first conclusive evidence came from the reflectance spectroscopy, which was done using MQ. Basically, hydroxyl was seen, OH or oblique H2O was discovered using Chandrayaan-1 moon mineralogy mapper. And then you have a series of missions. You have an impactor, then you have other missions which are orbiter missions which are running, and you know that you have Chandrayaan-2 there, and then you have Chandrayaan-3, which is the Chandrayaan-3 lander, and then the rover, which we will hear from very soon, in about 3.5 weeks' time. And then you can see a series of, how moon is, there is so much interest in lunar exploration, and this is what I wanted to show you in this slide. And there are major programs, for example, the lunar program, okay, where you have sample return, and then you have the Artemis crewed program, which is planned in 2024 in the US. And then, of course, you have landers and rovers. So, lunar research is not over. Okay, and now we wish to look for resources, and we wish to understand where are the volatiles, where are the resources, and of course, then these questions: did the early flux of impacts peak at 4 billion years ago, or did it decay exponentially with time? This is only possible when we have samples returned from the moon in future, which look at those periods. Okay, so then we wish to assess the nature of the moon's interior, just as it was done using the InSight mission recently for Mars, and then test the models for differentiation, crust and mantle, and we wish to know the composition and mineralogy of the lower crust and mantle, confirmation of the polar hydrogen deposits, and determine the history and water and other volatiles. Basically, ascertain the volatile transport process. Is it there, or is and then assess the mineral resources of moon, and then the South Pole Aitken Basin, which is so relevant because that places limits on the early impact history, and it is the deepest basin. So it should expose the the upper mantle, or the lower mantle. Now we move on to Mars. In the last 10 minutes of this, already it's about 4, so I have skip one slide here. So this slide, it shows you, this is from JGR, this is from a paper, but this shows you how the chemical environments, now we are going to Mars, okay? So there the question is, firstly, did life exist on Mars? This is still unanswered. And then was habitability of the environment in the first, up to about the Noachian area, particularly if you look at, there are 3 areas which are listed here, right? So the boundaries are not so well defined because there are no absolute ages. You need to calibrate the lunar, you need a complete calibration. Part of it is there, but you need an entire calibration of the lunar, the lunar curve, basically. If you look at the crater counting curve, basically, that the crater counting method is not absolute. It is a relative method. So here, and in the case of Mars, one need, this does not exist at all because you don't have absolute ages or return samples as you have from Moon. So you have materials, you see sheet silicates, okay? This is all telling about water, carbonate deposits, for that you need water, chloride deposits, okay? But then it changes to the gypsum. So in the Amazonian, which is basically, the last 3 billion years or so. So chemical environments have changed. Initially you have clay formation, you need water. then you have sulfates, and then you have anhydrous ferric oxides in a very dry environment, which is there, and that's why you have that color in Mars. Some of the interesting discoveries, I've just listed a very few prominent ones. Diverse environments with water-related minerals, remnant magnetism, existence of near-surface ice distribution, atmospheric methane, then that is still contested. So some measurements were there, but on the surface, but whether it is there in significant proportions and how did it arise? So all those things, geological, sources geological or biological, don't know. So then what did, we would like to address these questions. How, when, why did environments vary through the Martian history? Did any of them host life or its precursors? How has the Martian climate evolved through time? What are the inventory of carbon compounds and the trace gases? And what are the processes that govern their origin and evolution? What is the internal structure? This was somewhat addressed in the InSight mission. And then what are the nature, ages, and origin of the diverse geological units and aqueous environments which are seen from orbital and landed data, and were these habitable? So one work which I just want to show you, this is from remote sensing data, right? So you can see lobate, like lobes, basically these features in the one which is at the bottom left-hand corner. And this basically, Rishitosh Sinha in PRL has shown, this was something new, which was shown about 7-8 years ago, that there are 3 phases, major phases of glaciation, in the Amazonian era. So this is based on the different geomorphic features. So lobate debris apron is linked with major phase of glaciation. Then you have concentric CCF, concentric crater fills. And then you have viscous flow features and gully, which is associated with minor phase of glaciation. So this was, this was documented to our knowledge for in such detail for the first time by our group. And then these are the missions, the orbiter and the lander, and Mangalyaan, or Mars orbiter mission, was launched. You can see in 2013, and it has provided a lot of interesting data. Then Mars is still unexplored in the sense that you have no sample return missions thus far, and also there are plans in the MMX mission to look at the Martian moons. Okay, and then there are these. I mean, many questions are left unanswered, and some of this will form the basis for future missions as well. And this is where I wish to end. I hope this was an interesting talk, and I hope some of you will develop instruments which will be flown in future missions and also contribute to the future planetary science in the next few decades. Thank you.